Good day, dear friends. Hope all of you are doing well. I am Pranasish and I am here to make an honest effort to invert the idea of unit tangent in a curvilinear motion. With the knowledge of unit tangent and unit normal, you can understand in much better way the velocity, the acceleration and the likes which might have already been introduced to you. Let's learn the let's get the idea of unit tangent in a curvilinear motion. Let O be the origin. This is a curved path followed by a particle. The initial position of the particle is A. The position vector of point A is vector r. Thus we can write OA vector is vector r. The particle moves along this curved path to another point B. The particle makes a displacement AB vector, and let AB vector be delta vector r. Then the position vector of point B will be equal to vector r plus delta vector r. Thus we can write OB vector is equal to vector r plus delta vector r. This is the angle by which the curve curves as the particle moves from point A to point B. Chord AB, the length of chord AB gives us the magnitude of the displacement made by the particle. Thus we can write chord AB is equal to the modulus of delta vector r. The arc AB, the length of the arc AB gives us the distance traveled by the particle. Thus we can write arc AB is equal to the distance traveled by the particle, and let it be delta s. The arc is always greater than the corresponding chord. Thus we can write the magnitude of delta vector r minus delta s is not equal to 0. If point B were closer to point A than it is, then the difference between the magnitude of delta vector r and delta s would decrease. If B were so close to A that point A and point B could not be distinguished from each other, then delta s would tend to 0. Let's redraw. This is the origin O, this is a curved path. A is the initial position of the particle, it's vector r, and B is very close to point A, and the displacement is as usual delta vector r, and OB vector r plus delta vector r, and this is the angle delta theta. Here delta s tends to 0. And so delta theta, by which the curve curves, is also tends to 0. Now we see here that limit the magnitude of delta vector r minus delta s would tend to 0 as delta s tends to 0. If we divide this expression by delta s, the final expression would also tend to 0. And from this expression we can write limit the magnitude of delta vector r upon delta s minus 1 tends to 0 as delta s tends to 0. And from this we can get the magnitude of delta vector r upon delta s when delta s tends to 0 is equal to 1. Now let's identify the direction. Here chord AB gives the direction of the displacement delta vector r. If we produce the join of point A and point B, we get the direction of the tangent drawn to the curve at point A or at point B. Thus, the minute displacement is directed along the tangent drawn to the curve at point A. Then limit delta vector r upon delta s when delta s tends to 0 would have unit magnitude and the direction is along the tangent drawn to the curve at point A. Thus, we get the unit tangent. We can write here unit tangent. And from calculus, we reduce this expression to d vector r ds is equal to unit tangent. And this is the expression for unit tangent in the curvilinear motion of a particle. And it can be defined as the rate of change of position with respect to the distance traveled by the particle. Hope you've got a clear idea of unit tangent. In the next video, we'll get the idea of unit normal. Sit tight and wait for that. Thank you.